Hey. Hello, all. I think you all are kind of getting just let into the room now. So we're going to start in just a few minutes. But I'm Miriam, and this is my colleague Nick. We'll be introducing ourselves a little bit more in just a bit, but welcome. We're really glad to see there's a really nice big number of folks who registered for today's webinar, which is delightful for us because we love to nerd out about hexagons, and we're glad that you do too. So we're hoping that we'll be able to have, kind of a good discussion and good overview of H3, and we'd love to hear from you all as well too. So we'll get started in just about 2 minutes. Let's give time for folks to jump in. It's always kind of a funny thing when you're like in a big room, but you can't see anyone else. But we can see the numbers climb up as people come in.
Feel like this is the reality of presentations these days. It's all
It's funny. Yeah. When was, Nick, the last time you did an in-person in a room filled with people presentation?
geez, probably at least a year and a half ago, and
Yeah,
maybe 2 years ago now.
yeah, I know. I can't really fathom it. Like it was sort of cool with when we did, I guess when was that, last month, the Foursquare all hands, and there were some of us in a room, and I was like, whoa, we're all in a room, and like clapping to hear people clap and not just the silent claps that people do on like Google Hangouts and stuff. It's very funny. But yeah, welcome to those that are joining. We're seeing all the attendee numbers go up. So we're going to get started in just about a minute. For those that are getting logged in, I just wanted to cover a little bit of housekeeping. So we'll kind of just be chatting a little bit until 1 p.m. So for folks that are here with us today, we are really interested to hear kind of your questions. And as you can kind of see probably on your right-hand side of the screen, you have your sort of panel, the GoToWebinar panel, and there's a questions box in there where you can share questions with us. We do have time allocated at the end of the presentation to go through your questions, but I would actually encourage you to just chat in questions throughout as we go. What we'll be doing is if you ask a question that I'll kind of be monitoring, and if I think that it's sort of relevant, I might chime in and actually interrupt Nick and say, hey, Nick, we just got a question that might be relevant here. Otherwise, we'll wait till the end and we'll kind of go through them, but just feel free to be chatting in questions throughout the presentation. And for those that logged in more recently, I'm Miriam. I'm a product marketing manager with Foursquare, and we're super excited to have all of you here today talking about hexagons and H3. And with that, I will maybe pass it over to Nick to kick us off.
Sure, I'm happy to get started. So welcome everyone to the power of hexagons, how H3 is revolutionizing geospatial analytics. I think there's a certain amount of hyperbole in the title of the talk, but I also think that hopefully, if you're not familiar with H3, this will open some windows on what a geographic grid system can do in geospatial analytics. And I have seen, in some cases, whole companies that are starting to build major systems based around H3 as their main geographic approach. So I'm excited to talk to you today about hexagons. So a little bit about me. My name's Nick. I'm a senior staff engineer at Foursquare. Previous to Foursquare, I was at Unfolded. I'll talk more about that in one sec. And I spent 5 years at Uber, where H3 was originally developed. And prior to that, I worked in startups, I worked in nonprofits and NGOs, and I've done, many years as a software engineer, slightly more than I like to count these days. Many years in mapping and data visualization specifically. And I've worked now for, I'm going to say 3 or 4 years on H3 and H3.js. One of the core maintainers of the H3 library. And I'm secretly an English major, though I start to think that that gets less secret every time I say it. So I mentioned Unfolded. As some of you may know, I'm not sure who here is coming out of the Unfolded community. Who here is coming out of the Foursquare community? But I previously worked at a startup called Unfolded, and several months ago, Unfolded was acquired by Foursquare. We're now part of the Foursquare family. Unfolded is primarily a company dealing with geospatial analytics, and Foursquare has an enormous amount of geospatial data that's really exciting to work with. So we're really excited to start applying some of the technologies that we developed at Unfolded to Foursquare's data assets and to their deep knowledge about location data. So just to give you a quick outline of how this webinar will go, this is the intro. You're in it right now. And then I'm going to mostly focus on talking about geographic grid systems in general, and then talking about H3 specifically. So this is really meant as something of an introduction if you aren't familiar with how grid systems work and the kinds of analysis you can do there. And if you aren't familiar with H3, I'll go through a lot of the core principles involved, some of the core choices we made when developing H3, and then go through some examples of how you can use H3 in practice for a real analysis. And at the end, we'll have Q&A. So I think Miriam may have mentioned, but if you want to ask a question, please paste it into chat or into the questions box. I'm not sure which is easier in this context. And we'll get to those at the end. So I'm excited to hear what you have to ask as well. So let's jump right into it. What is a geographic grid system? Perhaps the best place to start is with a truism that we all know about the world when we're doing geographic analysis, which is that real world data is messy, and the real world itself is even messier. You know, there's in this picture, there are many different elements, far too many to count, and which ones you care about will change depending on the kinds of analysis you're doing. You know, some people will look at this picture and care about the buildings. Some people will care about the streets. Some people will care about the cars on the road. Some people will care about points of interest that you can't see, but that are located in this geographic area. In order to deal with this, we really need abstraction. This brings me to one of my favorite quotes about maps from Marc Monmonier. Not only is it easy to lie with maps, it's essential. And what he means by lying with maps is that every map has a lot of compromises and a lot of abstractions, and you're choosing what to show and what to hide. So maps are taking this messy world and they're abstracting it into a variety of simpler forms. Anyone who has worked with geographic data is probably familiar with these. You have point locations where they're just specified by a latitude and longitude. You might have lines, roads, routes, transit, other kinds of features. You have polygons, administrative boundaries, footprints, other kinds of things defined by their area rather than by a single location. And there are other kinds of abstractions as well that people use. But this is still really messy. If you look at, you know, a map like this Mapbox base map over here, it has a variety of different features. Some of them you may care about, some of them you may not care about. There are a great deal of different sizes, shapes. It's very hard to bring these things together into some kind of analysis. So geographic grid systems, also known as discrete global grids, apply a different kind of abstraction. They are dividing the world into uniform cells, uniform in shape, uniform in area, and they move everything on this map into this common unit of analysis. And what I like to think of this is it takes this messy real world space and moves it into this super clean mathematical space, which allows us to work with the data in ways that are very difficult if you're working with real world features or even abstractions that are closer to the real world than the grid. The other great thing about grid systems is that they aren't biased by natural or human processes. So they don't necessarily follow the natural features of the land. They don't follow administrative boundaries, and they don't come with the baggage that those things have and bring along with them. So you don't necessarily have this bias, in some cases, these biases of history or legislation or building codes that affect the built landscape, and you don't have the biases of the natural world, which may not be relevant to your analysis. And then because they put everything in a mathematical space, they support a variety of new types of algorithms, things that you could, in some cases, do in, with traditional geographic data formats, but in many cases are much, much easier both to develop and to run efficiently on a geographic grid system. A little bit of comparison, because these are the things that these are a couple things that people often use when they aren't using a grid system. Frequently, people might use administrative boundaries. In the US, that might mean counties, states, zip code areas, or census areas. Other countries have comparable units. And compared to administrative boundaries, grid systems, well, for one thing, they have comparable areas. So if you look at these counties on the right, you can see that in urban areas, you tend to have very small counties, densely packed with people. In more rural areas, I'm looking at Nevada, you have like enormous counties, in many cases very wide and empty. These are largely based on issues of history, issues of legislation, issues of population density, in some cases things that no longer even apply. And one thing that really comes up when you're working with administrative boundaries of any kind, whether they're legal administrative boundaries or whether they're produced by some other process, like the idea of neighborhoods, which are usually defined by the real estate market, they're always based on some use case that's frequently not yours. So counties, for example, or states have this strong historical background to this, core focus on different laws, different policies enacted by the governments, things like that. And you may or may not care about that. If you don't care about it, then these are incredibly arbitrary boundaries. And the fact that they vary widely in size and shape can be very confusing and difficult to handle in analysis. Another option here is to do ad hoc bins. So many, geographic information systems support binning on some level. It can create hex bins at any size or square bins at any size. And that can be a really useful way to group your data. But these things aren't stable. So it's very hard to share that kind of analysis with someone else and join data that you've put into ad hoc bins with someone else's ad hoc bins. By definition, these things don't have any common identifiers. They don't have any common way of joining them. And when you try to join them, you usually have to go through a great amount of acrobatics to make that actually happen. So while binning in general is something really well supported by a grid system and really well supported by ad hoc bins, the grid systems bring this whole new range of stability, unique identifiers, easily interoperable across systems. I've been talking about grids and grid systems. One thing I want to emphasize here is that a grid system is actually usually made up of multiple grids. So this is true for H3, it's true for many other grid systems. The multiple grids usually have different resolutions or different, you could say different granularities, where you have grids at different sizes, and you can change the size of the grid according to what's necessary for your analysis. Often you have a hierarchical relationship between grids. So you have a large grid that contains cells in its child grid. And often that can go down, sometimes ad infinitum, sometimes down to a fixed level. So H3 is the grid system I'm here to talk about, but it's not the only grid system. There are many other grid systems around that have been used for a while. Probably the most common is simply the graticule, which is to say the lines of latitude and longitude, which divide the world up into grids that are frequently shown on maps and often are used as a simple way of dividing that map up into roughly equal cells. Another one is web Mercator tiles. This is a technology frequently used on the web to divide up maps into pieces that can be independently served. You can use the identifiers for the tiles as another way of dividing up the world into square grid cells. S2 is a little bit more of an involved and true grid system. So this is something developed by Google many years ago at this point, using a square grid cell or a quadrilateral grid cell. And it has some advantages and disadvantages as well. And finally, you have H3, which perhaps is the newest kid on the block in the discrete global grid market, which uses hexagonal cells to form its grid. So one key question here that I get asked a lot is, why hexagons? I think many of us are probably more familiar with square grids, and in some cases, square grids are, very easy to work with. Why do we choose hexagons to go with to use for the H3 grid system? Is it just because they're cool, or are there more deeper reasons? So there are many shapes that you can use to tile the plane, and maybe somewhat fewer shapes that you can use to tile a sphere. What makes one shape better than another? So why didn't we choose geese and fish for our grid system? This is obviously an absurd suggestion, but it's worth thinking about the reasons why it's absurd. What makes these shapes silly and not particularly useful for a grid system, and other shapes better? So I've come up with a list here. It's probably not an exhaustive list of all the things you might care about when you're choosing a grid cell. And these are all things that suit a variety of use cases. So a good grid is going to serve a great number of analytical use cases, not just one or two. And therefore, it has to have properties which are going to be amenable to many different users, many different use cases. Initially, it's really useful to have uniformity in the shape you choose. So these are all different shapes that can tile the plane, but not all of them are uniform. They're all uniform in shape. You could use that same shape, but they aren't uniform in edge length. You can see you've got an isosceles triangle, you've got other things here, and they aren't uniform in angles. In the extreme case of the cross, you have 90-degree angles and 270-degree angles in the same shape. Having these things, having this uniformity means that your grid is a little bit easier to deal with, that the points in your grid are going to be closest to the center of your grid cells. And having uniformity also just makes these shapes easier to work with. So the shapes that are commonly used for grid systems are these three: the regular polygons that tile the plane, a triangle, a square, or a hexagon. You also, I alluded to this earlier, you also care about how compact the shape is. And one way to think about what it means for a shape to be compact is how close all of the points are to the center of the cell. And you can see that in this example, the distance from the extremes of the shape and the closest parts of the shape are least in the hexagon. So the corners and the center of the edges in the hexagon have less standard deviation away from the center than is true for the squares or the triangles. So hexagons are an optimally compact shape among these shapes. Obviously, the most compact shape here is a circle, but circles can't tile the plane. You also want it to be optimally space filling. So a good way of understanding this is to say, if I took a polygon and tried to represent it with grid cells, how close can I get to the shape and to the area of that polygon? And it turns out, I'm not going to go through a mathematical proof here, but it turns out that hexagons are the best option here. Hexagons are optimally shape filling. They can come up with the best representation of arbitrary polygons, assuming that your arbitrary polygons are truly arbitrary and not fitted to a specific kind of grid. You also, for many algorithms, you want uniform adjacency. And what that means is that you want all the neighbors of your cells to be about equal. This matters a lot when you're doing algorithms that involve traversal, moving from one cell to another. And I'll go through what some of those algorithms might be later on. But you can see that there's a big advantage for hexagons here. Hexagons have 6 equal neighbors, whereas even squares have 4 equal neighbors and then 4 kind of lousy neighbors at the corners, neighbors that you can't really treat in the same way that you treat the neighbors at the edges. And obviously triangles are even worse. Triangles have 3 equal neighbors and and 9, you know, unequal or distant neighbors that they touch at the edges. So hexagons have a big advantage if you're planning to do algorithms where adjacency matters. Hierarchical relationships, as I alluded to, are also really important for grid systems because you frequently have hierarchical relationships between the layers of the grid. Hexagons don't do quite as well here because while they can have hierarchy, they don't have perfect containment of those children. So you can see that, you know, you can divide the triangle into 4 or more sub-triangles that are perfectly contained by the parent. Same with the square. Hexagons, you have to make a little bit of a compromise. We can do this compromise with a fixed margin of error between layers, but you can see that there are, if you were indexing points, for example, to a hexagon cell, you can see that some of the points that you would index to the children would not end up indexed to the parent. So there's a little bit of error between the different parent-child layers in a hexagon grid, and that's something you have to come to terms with if you're going to use it. It might not be as well suited for types of analysis where exact aggregation is important, for example. And finally, for a global grid system, for a grid system you're planning to put onto the sphere of the Earth, or oblate spheroid of the Earth, you also care about distortion. So you care about low shape distortion and low area distortion. And if you're familiar with mapping, you might understand that this is really a function of the projections you're using. And one of the things that makes a projection have lower distortion is if it's really applied over a smaller area of the Earth. So in general, a projection is a way of taking a flat plane, or rather taking the sphere and representing it or part of it on a flat plane in a way that's minimally distorted. I've shown these polyhedra here because the way that grid systems are usually created is to start with a polyhedron and to use a different projection on each face of the polyhedron. You can use something like a cylinder, the first thing here, and that's what many map projections use as their projection base, but you get a lot of distortion, especially toward the poles. Anyone who's familiar with the downsides of the Mercator projection, you know that you end up with these singularities toward the poles that are very difficult to deal with. That's not a great idea for a global grid system that's supposed to be uniform across the globe. So the more faces you have in your polyhedron, the more projection surfaces you have and the less distortion you have. And these Platonic solids are the only options if you are looking to have a uniform face shape. So these are all polyhedra that have the same shape on every face. Again, that simplifies the creation of a grid system, makes analysis much more uniform, is generally a good idea. You can see that the one that has the most faces here is the icosahedron, which is a 20-sided face. You might know this as a D20 if you've ever played role-playing games. And it has triangular faces. Only one of these polyhedra, the cube, has a square face. And that makes a difference when you're choosing grid cells because you can fill a triangular face very well with either triangles or hexagons, but you can only fill a square face with squares. So if you're using a square grid cell and you want it to not have crazy singularities around the edges of your projection surface, then you basically need to use a cube, which means you only have 4 projection surfaces and you're going to have greater distortion. So if we look at all these things together, hexagons come out pretty high on a lot of these key features. We have to compromise a little bit on perfect child containment. We have to compromise a tiny bit on uniform shape, as I'll get to in just a sec. But overall, a hexagon is a great choice for a distributed grid system. This sort of brings me to a pet peeve, if you will. I often hear slightly dismissive opinions saying, H3 or hexagon grids in general, people just like them because they look cool. And I would like to submit that maybe they look cool because they are cool, because hexagons have all these features that actually make it not only visually better, but mathematically more of a solid choice for doing work with data. They're a better representation of the data that they are used to represent. And I would even go further to say that, our brains have this incredibly deep and powerful visual processing ability. And we can see a lot of things pre-attentively without thinking about it that you process with your brain well before, in the visual centers of your brain, well before you process it in the analytical portions of your brain. And I think that hexagons, part of the reason they look cool is because we can see visually that they are a better representation of what we're looking at. If you're trying to represent, say, a polygon with a set of hexagons, it looks more like that underlying polygon than square cells would. So I think that the idea of looking cool, perhaps there's actually some validity there, but don't undersell how important that is, because actually that's telling us something deeper than you might think about the capacity of the grid. So that was a lot about hexagons. I did promise that there was going to be a lot of hexagons in this talk, and maybe that was more geometry than you were prepared for. But I would also like to get into the H3 library itself, where we've used this idea of a hexagon grid and actually implemented something that can be widely used. So this is a quick picture of how we've constructed the grid. You take an icosahedron, you lay that icosahedron on top of the globe. We owe something to Buckminster Fuller here because he was a well-known polymath, I guess. He did a lot of different things, an engineer and a geographer, among others. And he was very interested in different kinds of projections. One of the things he figured out was how to lay an icosahedron, how to position an icosahedron on the globe so that almost all of the vertices are over water. And that's an extremely useful feature if you mostly care about land, because you can avoid the singularities that you get at the vertices of the icosahedron. So if you look at the face of the icosahedron, we can then divide that up into hexagons and half hexagons. And then we can take each of those hexagons and divide it up into 7 children and keep on going down and down and down. The H3 grid has 16 resolutions. The largest, as you can see, is maybe roughly continent sized or a little bit smaller than a continent. The smallest gets down to below a square meter. So as you subdivide, you get smaller and smaller, and you have many different choices as a user of H3 about which resolution to use. I did want to talk very briefly about the singularities I mentioned, which is that we do have 12 pentagons in every layer of the H3 grid. And you can see we can't quite get around this because you have 5 faces of the icosahedron that come together at every vertex. We need to represent those somehow, and we end up representing them as a pentagon. You can think of this in terms of the grid cell. It's basically just a hexagon grid cell, but it's missing one axial dimension. So it's roughly the same kind of cell, but when I say roughly, you do have to deal with it differently in analyses that actually hit pentagons. The H3 library does most of that work for you. Most of the time when you have to deal with pentagons, the H3 library will take care of that for you. And as I mentioned, almost all of the pentagons are on water. So if most of your analytical needs are on land, you can almost always simply ignore them. Maybe I'm being a little bit glib there if you're doing, full-scale planetary weather analysis. Most people aren't going to have a lot of trouble with the pentagons in the grid. So this is the grid as it looks. This is the first 2 layers of the grid system laid out on different parts of the Earth. And this grid is represented by the H3 library. The H3 library is an open source project that was started at Uber. And when we built it at Uber, we decided to build it in C, partly because C is very fast, but mostly because C is very portable. So building it in C allowed us to easily create versions of the library in many different languages. So you can now use this library. You can use it in Python, Java, JavaScript, Go. There are bindings for databases, including Postgres and BigQuery. Building it in C, in this sort of low-level language, allows many other use cases where you can bind to the C library, get all the speed of the C processing, but get familiar interfaces that you might want to work with. So if you're a data scientist, you might be using the Python version. If you're building a web application, you can do this in JavaScript. You can even do it very performantly in the browser. And that's something that underpins a lot of the work that we've done at Unfolded and now at Foursquare to build web-based applications that deal with H3. I won't go into detail about the library itself. Maybe not everyone here is going to use it as a programmer right away. But just to give you some sense of the kinds of things that H3 does, it's mostly handling these low-level functions around the grid. So the most important ones are indexing. So taking points on the map and assigning them to a cell, and then going the other way and taking a cell and telling you what its centroid is, what its boundaries are. There's also functions that define the hierarchy, so being able to move up and down these levels of the grid. There are functions around traversal, especially finding all of the nearest neighbors to a cell within some given distance, or finding the path between two given cells. And there are functions around regions, particularly moving from a polygon to a set of cells, or moving from a set of cells to the bounding polygon. And there's a variety of other utilities for dealing with the grid around inspection. There's a set of things around dealing with edges specifically as unique objects. There's measurement, and there's a bunch of other things that you'll find if you look through the library and start playing with it. To give you a taste of how we actually use this in practice, I wanted to go through a pretty simple analysis just to give you a sense of what you can do with H3 when you're doing geoanalytics. So I started off with this point data set. This is from Oakland Crime Watch from 2020. And I live in Oakland. Crime is always something that we're concerned about. There also tend to be a lot of specious claims about crime in Oakland, either that it's a high crime city or that crime is getting worse or what have you. So I always like to look at it from an analytical perspective rather than from a sort of scaremonger perspective. Interestingly, some of the first web maps I ever saw, really data-focused web maps, were crime maps of Oakland. There was a well-known application at the time, might have even been called Crime Mapper or something like it, that just showed you, all the recent incidents on the map of Oakland. And what I always really disliked about it is when you see a point data set like this, the only impression you get is that there's a lot of crime. There are many points here, but it doesn't really tell you much about patterns or trends or anything that you might want to know from an analytical perspective about these different incidents. So the first thing I usually do when I'm dealing with a point data set and I want to bring it into H3 is to index every row. And the first choice you have to make is what resolution you might choose to index at. So the higher the number of the resolution, the finer the grid level. This is at res 9, which is a bit larger than a city block. And I can start to aggregate everything within these cells and get a better overall picture of my data set. So, in this case, I'm taking every point within a given cell, I'm grouping by that cell index. So every cell has a unique identifier that we can easily use for grouping. And I'm aggregating, in this case, by count. So this is just a sort of heat map, in this case, of these incidents across the city of Oakland. I might choose a different resolution at this point. So this res 9 felt a little coarse when I was looking at it. I was interested in a little bit finer grained data. So I can bring this down a resolution. I'm re-aggregated it at resolution 10, and that maybe gives me a little bit finer grained picture of how these incidents are distributed across the city. Obviously, I aggregated by count, but there are other types of aggregation. This is an aggregation across a categorical value, the type of crime. I wanted to get some sense of how the type of crime might vary across the city. It's a little noisy here, but you can definitely see some trends. So this brown up in the north section of the city, this is mostly auto burglary. So a lot of, smash and grab, car theft in this area. Right here, this is like downtown Oakland. A lot of people are parking and then having their cars broken into. I say a lot, but that's the more frequent type of crime there. Um, and the blue, I think, dark blue is residential burglary, light blue is perhaps vandalism. So over here you have sort of more residential crimes, more crimes focused on cars. Down here, the orange is more like felony assault. And there's a couple of, I think pink down here is weapons charges. So you get a different kind of crime in East Oakland down here at the south end of the city. And you can see the spread and how it changes over the city a little bit when you're doing a categorical aggregation. If I take these counts and I look at them, one of the things that you frequently want to do as an analyst is to say, well, this looks great, but do I know that it's not just a population map? Do I know that we're not just looking at population density with crime as a proxy for that measure? So one way to address this is to look at population and then to normalize by population. So you can take the polygons that you get from census data, either block groups or even census blocks, and you can use that as the basis for a new H3 based data set. This is actually a data set that we've sort of prepared in Unfolded Studio, the application that Unfolded provides, and something you can easily bring in. And what it means when you have this set of data already aggregated into H3 hexagons is that you can easily combine data sets. So this is one of the real benefits of using a grid system, any grid system, but I think it works very well for H3, is that it allows you to very easily unify data sets that might come in as points, as polygons, as lines or raster data, all these different formats, which can be very hard to join together a priori. You can bring them into a common unit of analysis, a cell at a given resolution, and then you can do cell arithmetic. This is sometimes called raster arithmetic, but I don't want to confuse the traditional raster data format here. You can do cell arithmetic, where you're basically doing arithmetic. You can think of these as a sandwich of layers, and within each cell, you now have a variety of different metrics from different data sets that you can combine in a way that makes sense. In this case, we can normalize the crime by population simply by dividing by the population, and we get this different picture of normalized data. Here you can see there's a higher concentration of crime per population down on the sort of southern border of the city, especially in the downtown area. You start to wonder, maybe that's because there's more crime, maybe because these are commercial areas with a low population, but it's definitely a different kind of view on the data that would be difficult to get to if you didn't have access to a population data set that was easy to join. Normalizing by population can be a really difficult thing in many analyses. H3 makes it comparably simple. You can simply stick the different layers together, join on this common identifier, and then do any kind of math you want to across the row. Another thing I wanted to look at here, if you look at this, this original data set, it's pretty sparse. And if, for example, you're approaching this data set as a homeowner, you might be interested if there was crime right there on your block in this very small, well-defined area, but you would also be interested in crime the next block over and the block over beyond that. So one really easy algorithm that H3 is particularly well suited for is smoothing, where you basically spread out the values in every cell by averaging that cell with its neighbors. And this gives you a broader and smoother view of the data over the area of analysis, and allows you to interpolate data in some places where you didn't have data before. So you can see this is a much more sort of dense view of the city. If I'm looking at, say, real estate values or something like that within this city, I can pretty easily see whether there's been crime nearby. You can do multiple smoothing passes as well to get an even sort of smoother view. It really depends on the type of analysis you're doing. I didn't do an example of it here because crime isn't truly continuous, but if you think about something like temperature, which is continuous, You can also create an entire surface here. So instead of just smoothing, you could interpolate values between all of your known points. You can create a smooth surface in which every grid cell has a value, and you can use that potentially for other analyses or to interpolate data in places where you don't actually have measurements. So we're coming up on time here, but I hope that gave you a taste of the kinds of things you can do with H3. There are a lot of other kinds of analysis that a grid system, and especially H3, is really well suited for. So spatial indexing is obviously the core bread and butter of a grid system. And simply being able to do this in a online database is frequently really useful. You can quickly find points nearby. You can quickly do a simple radius search. Those things can be extremely useful if you want a fast system with some sense of geographic lookup. There's a lot of other things here I won't go into. I did want to show an example of clustering, but my attempt to whip this up at the last minute didn't come out as nice looking as I was hoping. But many of these are really amenable for H3. Suitability analysis, which I won't go to in detail, is basically taking this idea of merging layers together and putting it on steroids. So suitability analysis is using many different features to do something usually like site selection, finding the place that's most suitable for your use case in a city. If you want to say, find a place to put a new store or something like that, you can take, just as we took population and crime and stuck them together, you can imagine taking 20 other data sets, also sticking them together, applying weights to each data set, depending on how much you care about those different things, and then coming up with this smooth surface in the H3 grid where you can easily find places that might be particularly good or particularly bad for your desired use case. And there's more that I won't go into here, but all of these types of analysis, many of them you could do on other kinds of geographic representations, but almost all of them are much easier to do, easier to implement, easier to run in a fast and efficient manner in an online system, even easier just to reason about when you're working in a grid system. I want to close just by shouting out to Studio, which is the application that I built all these images in. It's the application Unfolded and now Foursquare provide for geographic analysis. It's free to sign up and really easy to get started. It's built on Kepler, but it has a lot of additional features beyond what you may be familiar with if you're familiar with Kepler. It's not only based around H3, but it has really good support for things that do involve H3. And so it allows you to really easily work with a variety of different kinds of data sets and to bring in some of these H3 analyses. So I'd encourage you to go and check it out. Thank you. That concludes my webinar. I hope you learned all the things you were hoping to learn about hexagons, and I'm eager to hear your questions.
Yay! So I will insert the round of applause that we would be hearing if we could all magically be in person.
Thank you.
Yes. Thank you so much, Nick. That was awesome. And for folks who are on the line, we have a little bit of extra time, so we'll kind of go probably until 2 p.m. Eastern. So if you do need to drop off, no worries, you'll get a recording and we'll kind of go through the questions. So don't worry about that. Nick, we got a bunch of questions. I think you're gonna love all of them. And so thank you everyone who's been chatting them in. There's some that I'm excited about, but we'll just dive in. I'll try to get through these. So I think right now, so far we have about 6 questions. So we'll see if we can get through those, but feel free for other folks, you can still chime in and go ahead and chat those in. So Nick, one question is, how does H3 manage large data, like everyday 100 gigabyte data getting inserted? Do I need to add more clusters of machines? And is there any best practice for this?
That's a really good question, and it goes, obviously beyond the kind of things that we talked about in this presentation. But I think H3 is in fact really well suited for distributed systems. Again, that might be true for a lot of grid systems, but I think what you can frequently do in this case, it really depends on the kind of data you're dealing with. There's a couple different ways to look at this. One thing that H3 works really well for is key value stores, which like for example Cassandra, which can be scaled at a really large scale pretty easily. There's a well-known set of ways that you scale key value stores, and because H3 gives you a unique identifier for all of your data, it makes it very easy to associate data with an H3 cell and then quickly pull it back from a system like Cassandra. So that's one answer. You can also do a lot of sharding or partitioning of your data based on coarser resolution cells, and then include the data for finer grained cells, in those shards. So you might, partition your data using the H3 grid at some coarse resolution, like 2 or 3, and then include the data within those shards at a fine-grained resolution, allowing you to pull out different parts of data depending on what part of the world you're looking at. It's hard to go into more detail there without knowing more about a specific use case, but the overall answer is that grid systems are great for partitioning, sharding, and distributing data processing. Often it allows for parallel processing across each grid cell independently, if that's possible for your analysis, and that makes it much easier to work with very large data sets once you've indexed them to H3.
Awesome. All right, next question is, how can we apply H3 to remote sensing data? Can we place Sentinel-2 data into the H3 grid, for example?
That's a great question. That's actually something we're working on right now at Unfolded, is being able to easily convert raster data to H3. Conceptually, you can imagine, raster data is generally represented as pixels, and each of those pixels represents some land area. So conceptually, each of those pixels is essentially like a polygon, and you can treat it in a similar way to a polygon data set. One very simple and straightforward way, perhaps, of dealing with raster data is if you look at each raster cell, take the centroid, find the H3 cell that it applies to, and then you can aggregate those raster cells by H3. That's one way that I've done this before. There are faster and more efficient approaches to converting raster data to H3 based on image processing that leverage the GPU a little bit better, and that's something that we're actively investigating at Unfolded right now. The short answer is it's not something we have implemented in the product yet, but it's something that we would like to see in the near future, because raster data is traditionally very difficult to work with in conjunction with other data sets. It's very difficult to take Sentinel data and combine it with a Polygon data set. But if you have both of those things converted to H3, which is really not a great step beyond what's possible, even right now in our system, suddenly you have something that you can easily join together and play with. So not something that's supported right now in our application, but certainly something that's that works well with H3, because you can go between the raster and H3 representations pretty easily.
Cool. Awesome. All right, we have some questions about, so sort of getting into the geometry side of H3. Have you thought about a 3D grid of rhombic dodecahedrons? Could be useful for industry and science like mining, ocean mapping, oil and gas, etc.
Believe it or not, we have. We have thought about using H3 in 3D contexts. I think you would probably end up needing another shape if you wanted a truly uniform 3D grid. Mostly what I've seen people do in contexts where, essentially in contexts where elevation mattered, is to add additional elevation metrics on top of H3, so that you're sort of representing a column. If you think about the H3 hexagon as a column of air or a column of land underneath, you're representing that, and you're taking slices of that as part of your 3D grid. So it's not really three-dimensional in the 3-axis sense. It's all still, you can think of it as columns radiating out from the center of the Earth. Those are not uniform in volume, because as you go out, they get bigger, and as you go into the Earth, they get smaller. That's probably the best we can do with H3. I have heard of people working on uniform volume 3D grids, it's tricky to have that work well on the surface of the globe, is the bottom line. You can do it within limited areas. It might work well for some, aviation use cases, for example. Uh, but, H3 can't really give you equal volume in that context. You would probably need a wholly different grid system.
Cool. Awesome. All right, some questions about sort of hierarchy and parent-child relationships. So for H3. So regarding the child containment issue, are there H3 library functions to help with that, i.e. returning the percent of overlap?
Good question. Not yet, though that has been a requested feature. We don't currently have a specific way to do that. Usually, this isn't perhaps the greatest answer, but in most applications where I've worked with, you can more or less ignore the overlap unless you're trying to do aggregations where the exact boundaries of the parent matter. That's really what it comes down to. If you're willing to take the boundaries of the child as the true canonical boundary of something represented by the parent, then you can do all your analyses just the way you would. The one thing that's a little bit harder there is sometimes displaying the parent. If you're displaying the parent cell and then displaying the points that come together to make that value, you'll see some discrepancy visually. But from an analytical perspective, if you just accept the idea that, let's say a res3 cell as projected into its res5 children has a non-hexagonal shape in its true canonical shape. This is a little bit hard to do without a visual helper here, but you can often do many types of analyses where that abstraction is fine. You have a unique identifier that refers to all those cells in the parent, and often for many different types of analyses, the unique identifier is all you need. So it really depends. But this is one place where H3 and any hexagon grid is going to be a little bit weaker than a square grid or a grid that uses quadrilaterals that can be perfectly divided.
Mm-hmm. And that actually, there's a question that someone else asked. So it's about, one competitive grid system is Google's S2. In what situation might you use H3 versus S2 and vice versa? So is that kind of an example, or would you add anything to that?
Yeah, so I talked a little bit about this already. I think that, one of the big downsides of S2 is that it has much greater shape distortion than H3 does. So if that matters to you in different parts of the globe, that might be a reason to turn towards H3. If perfect aggregation matters to you, then S2 might be a better choice if that's a really big part of your use case. The other thing, and I haven't actually worked with this in detail, but in some systems you can also do, because of the way the S2 index is created, you can do range queries with S2, which means that the index, like if you take a range of the index numbers, those will all be close together. And so you can do certain types of queries are faster against things indexed to S2 than things indexed to H3. There are similar things you can do with H3, but it's a little bit harder to implement. So I've heard people say that that's a benefit of S2. One huge advantage of H3 is that S2 is not generally available in all of the different platforms and languages that H3 is available in, and doesn't have the same level of current maintenance, doesn't have the same level of support that H3 currently has. So, I'm not going to say that H3 is always better than S2 because it's not. There are certainly use cases. I would say that H3 is a better general purpose library than S2. And especially if you don't know all of your use cases up front, that can make it a very good choice.
Cool. Awesome. Amazing. Okay, and you're getting lots of questions and kudos, Nick. So this is good. Thank you, everyone, for chiming in. So we had another question about hierarchies. Can you walk through the process for performing a hierarchy change? For instance, you showed the crime data at a 9 and then went down to a 10. Did you need to rerun your process to append the hex ID at the level 9 and then again at the level 10?
Yeah, so I can go back to this these slides. In this case, yes. There are actually, I mean, so there are two things I could have done here, and it depends a little bit on how expensive it is to re-index. Um, so what I actually did here was I took my original point data set and simply re-indexed it from resolution 9 and re-indexed it at resolution 10. In this case, think I had 7,000 some points. Oh no, it was more than that. I had 7,000 hexagons in the end. I had 55,000 rows. H3 is extremely fast at indexing. Rerunning that indexing was not a big deal. It might be a big deal in certain systems. Another thing you can do in this context so usually, let's put it this way, usually you want to index at the finer grain, and that allows you to aggregate up. So if I had data at resolution 10, I can pretty easily aggregate that data up to resolution 9, as long as I'm willing to bear with the margin of error that we talked about in terms of the parent-child containment. So, if it's okay for me that my resolution 9 cells might have a small margin of error compared to the resolution 10, then this is a reasonable way of doing it. The other issue here, which is true for any kind of regrouping, is what aggregation I'm using. Count or sum, it's pretty easy to go from a fine-grained resolution to a coarse-grained resolution simply by adding up all of the children. If I had a count unique or a mode like this, that's probably not going to be a valid reaggregation. So that's true for any kind of grouping you're doing, obviously. The H3 library provides easy ways to go up and down the hierarchy. So I can easily ask for the parent of a cell at any level, or the child, or all the children of a cell at any finer grain. In terms of how you actually deal with the data at those different resolutions, that's really going to depend on your use case. Some use cases, it's going to be fine to aggregate up into the parent. Some use cases you're going to want to re-aggregate from from your raw data. Several systems I've worked with, the approach was simply to pre-index. So if you have a large number of points in your database, when you ingest those points, you index each one at several different resolutions, and you work with them. Depending on what kinds of queries you want to do, you just query them at one resolution or another resolution. So that might be a way to get around this as well. When I was at Uber, I would say that we usually tried to pick a resolution that was a semi-standard resolution across the company. And the reason for that is that it just simplifies a lot of things if many of your systems are indexing at the same resolution. That's a lot less useful in a one-person data scientist analyst kind of use case. But if you're building a whole bunch of infrastructure around H3, it might be useful to pick one or two resolutions that are meaningful for your business and to standardize around those resolutions. In Uber, it was usually Res 9 when I was there. Was a granularity that made sense for most of the systems at Uber, given the kinds of businesses that we were business that we were running in those cities. But that may change widely. And in fact, even at Uber, there were cases where we had to go much finer or much coarser because the use case demanded it.
And on that note, someone was asking, is there any reason why 16 resolutions for H3? Like, why were those specific resolution sizes chosen?
So I didn't go into the details of the bit layout of the H3 index because I thought maybe that would be a little bit too technical. I can in detail if you like. But the bottom line is that H3 indexes are 64-bit integers, or rather they're represented as 64-bit integers. And we basically tried to stuff as much as we could into those 64 bits. And so you've got a set of bits at the beginning of the index that indicate the type of index it is, the base cell that this index is aligned to, the resolution that this index refers to, some other bits that are used in different scenarios. And then the rest of the bits are, if you think about, let me find a picture here that could help. So if you look at a picture like this, you've got this parent cell, and then you've got 7 child cells. Each of these basically has an index number from 0 to 6. And so that the actual index bits are set to say, I take my resolution 1 cell, and then I take child 3, and then I take child 2 of that one, and then I take child 3 of that one, and then I take child 5, the next one, down all the way to the resolutions. The reason why we picked 16 resolutions is because that's how much space we had in a 64-bit integer. And the reason why we picked 64 bits is because it was a good interoperable shape for a lot of different systems and could be fit as in a single, either pretty easily fit into a single string, but much more easily fit into a single integer that would work with many database systems without having to do anything special to represent the index. So we were limited in terms of how we could represent data within the index. Conceptually, you could add another 64 bits, make it a 264-bit pair, and keep on adding resolutions. But it's not something that we decided to support yet in the library. And to do that, honestly, you start getting into use cases where you are trying to index point clouds or something like that, which is not something that H3 is super well suited for. Right now the finest resolution gets down, as I said, to sub-square meter. It's pretty good for most analytical use cases. There aren't a lot of places where we've said, oh, I really wish we had resolution 17, because that would really give me something extra.
Awesome. And you all are amazing. Okay, we have a million questions and we only have a minute left. So I apologize, we're not able to get to all the questions. Honestly, they're fantastic. And I feel like we just need like a little H3 day, a little hexagon, full day session to go through all this. Maybe as a final question, I'll kind of combine. So a few people were asking about sort of resources and where they can learn more about H3. Just to give you a flavor, someone is asking, is there a good resource of how to use H3 with Kepler? Another person is asking about, is there an article for how to transform the point map to the H3 based map? And then a third question around resources is there a link about how H3 performs the polyfill function, an explanation that involves no code? So you don't have to answer all those in depth, but if there's anything off the top of your head that you want to offer for people and maybe generally around learning more about H3.
Sure. So all of the places on this slide are good resources. H3geo.org is the main H3 site. We have pretty comprehensive documentation. There's also a bunch of links to tutorials. Deep in the documentation, you can find some really deep breakdowns of how some of the algorithms work. I don't know if there's a description of the polyfill algorithm, but the very quick answer there is that polyfill basically looks at the centroid of every cell that might be contained in a polygon and then does a point and polygon check. And so any cell that has its centroid inside the polygon is included. Cells that don't have the centroid included are not. That has this nice property that contiguous polygons give you contiguous sets of H3 cells, and no H3 cell is assigned to more than one polygon in that scenario. There are other things you might want to do with polyfill, and we're actually looking at implementing that in a future version of H3, because a lot of people would like to have other polyfill modes as well. But the overall answer is check out h3geo.org for more information on H3. Check out studio.unfolded.ai to try out our application, which again is completely free. I don't know of a specific resource around using H3 with Kepler. I can try to look that up. Kepler certainly supports H3, has an H3 layer, but maybe has a little bit less support than Studio does. And I would also encourage everyone to join our Slack channel if you would want to hit us up for more questions, because we are generally there. We're happy to interact, answer questions, help out where we can. H3 also has a separate Slack channel, which you can get to from h3geo.org. Both of those are really good resources if you want to ask questions directly.
Mm-hmm. Awesome. Thank you so much, Nick. And yes, someone asked, can we get answers to the other questions answered offline? And I agree. I think joining either our Slack channel or if you want to join the H3 Slack, that's great as well too. Nick and I will take a look at the other questions that folks asked. So we have all of them, and we'll see if we can kind of share that out either via email, or we'll find a way to kind of respond to some of those if there are some quick answers there. But huge thanks to all of you. I really appreciate everyone's participation. I wish we had a full day of hexagons for you. But this was fantastic. And Nick, thank you so much. You have clearly ignited a hexagonal revolution, shall we say, or perhaps you've furthered the hexagonal revolution that has been continuing thanks to many, many folks.
Clearly one warrior in the revolution. I don't know if I like this metaphor, but you know.
Exactly. So yes, thank you all so much. And we hope to see you at the next event. So thanks, everybody.
Thanks so much. Appreciate everyone coming.